Actually, I want to just go ahead and see if I can finish some of the notes, and then we can push any questions that you guys have for tomorrow. Okay. So if you guys can turn to page 5. Actually, here we go. Okay, so we started talking about average value theorem. We didn't really get to an example yet, so let's work towards that. So average value theorem is just a rearranging of the area formula for a rectangle. The idea here is that we're going to find the area of, we're going to find the average height across all the heights of this graph. And the way we can do that is we can just take the area of this region divided by the width, and we're going to come across the average height. So the average height also represents the fact that there's a rectangle with that same, of that height that is going to serve as the area. The area of the rectangle here is going to be the same as the area of the shaded region. Okay, so let's look at example 1 and see if we can follow through applying this average value theorem. Okay, so part A, for example 1 says, find the average value of the function x squared plus 1 on the interval from 2 to 5. So think of your A value as your 2 and your B value as 5. Okay, and here I'm going to rewrite the average value theorem. So all we do at the beginning is we just go ahead and replace every A and B that we see with 2 and 5 and replace the f of x with x squared plus 1. Okay, any questions so far? Okay, so that's the same thing as 1 over 5 minus 2 is the same thing as 1/3. So with so many things going on with the coefficient, the integral, and the expression, the natural tendency that we really have to fight against is trying to plug the 2 and 5 into that x squared plus 1. Okay, the 2 and 5 and x squared plus 1, they're not ready to be involved with each other. So we have to take care of the calculus portion first. We've got to find the antiderivative before the balance can be involved. Okay, I know it feels easier to just plug in the 5 and the 2 into x squared plus 1, but it's not ready for it. Okay, we got to go through our antiderivative step. Right now, the only rule that we're going to be using for the most part is power rule. But as we gain more and more rules, we're just going to have to apply that antiderivative step. So we got to do power rule here, right? X squared plus 1, they're both ready for power rule. what does x squared become? X cubed over 3. And then 1 becomes 1x. Yeah. Okay, once you find the antiderivative, I'm going to just save that 1/3 for the end. I don't want to forget about that 1/3. That's true. But I'm just going to focus my attention right now on just that integral of x squared plus 1. So I found my antiderivative. Now I can work the bounds in. So to indicate that I'm about ready to use the bounds, I'll use a half bracket to the right and insert the 5 and 2. Okay. The 5 gets involved first. 5 gets plugged in for all the x's. Minus, parentheses, and now we can involve the lower bound. Okay, questions so far? Okay, so when we clean all this up, this is going to represent the area portion of the formula here. So we're trying to do some cleanup here. 125 over 3 plus 5 minus 8/3 minus 2. Combine these fractions here, I get 117 over 3 plus 3. Find common denominators, and that will get us down to 126 over 3. But that only represents the area component, right? To find the height, it's going to be height or area divided by the width. F of C. Now we got to bring in that 1/3 back into our calculation. This is my area, that's my width. Area divided by the width will give me height. So 126 over 9 comes all the way down to 14. Okay, so that's part A. So what that 14 tells us about the problem is that across my x squared plus 1 from 2 to 5, the average height, if I were to look at all the heights of that graph, the average height amongst all the heights of the graph is going to be 14. So now part B says find the c-value. Let me give you some perspective as to what we're trying to achieve here. So to find the c-value, let me draw out what we've achieved, or a rough visual here. So the x squared plus 1 graph is a parabola. Okay, 2 to 5. So imagine from 2 to 5, you have all these different heights for the graph. And then the average amongst all the heights ends up being 14. So that's what we found, right? We found that the average height for all the heights on this graph between 2 and 5 is 14. So now part B is saying find the c-value. So find the c-value just means we know that the graph is going to hit 14 at some y value. Where does it hit 14? What is that x value? So to find the c-value, basically just means set the function equal to the average value, in this case 14, and then solve for x. Okay, so our function is x squared plus 1. It's going to take that 14, insert it. And basically, I'm just trying to find the x value. I have the y value, just want to find the x value. Okay, take the square roots. Plus or minus shows up. So what's going to make sense, though? Our C value, can it be both positive and negative root 13? Okay. Technically, it will show up on the other side of the y-axis, but because our interval is only between 2 and 5, we don't care about any C value that lands outside the interval. So that's out. So we only care about what's in between the interval. From 2 to 5, C must be equal to our C value is root 13. So root 13, we know root 9 is 3. We know root 16 is 4. So we know somewhere between 3 and 4. Right? Okay. So that's average value theorem. We're going to do some practice with this, but any questions before we move on? We'll come back to it, but so I don't think it's complicated because all you do is once you plug everything in, you just have a coefficient with the integral, right? So you go through power rule, clean that up, and then involve the coefficient. But because there's so much going on, I think the tendency is we want to feel like we just want to get to the end, so we want to just involve the bounds with the expression. So make sure that we got to do the calculus first before the bounds can play a role. Okay, back page. Okay, so we first learned about first fundamental theorem of calculus, which we've been applying, right? Anytime we evaluate a definite integral, right, antiderivative, then plug in the 5 and 2, this is basically applying first theorem of calculus, right? You take the antiderivative and then you work the bounds in. So I abbreviate that as SFTC. A way to represent that is integral from a to b of f prime will turn itself into f of x, and then we just plug the upper bound in, followed by the lower bound. Okay, so that's first theorem. We also have something called the second fundamental theorem of calculus, and this is really going to highlight that relationship between derivative and integrals, that they're essentially going to cancel each other out. Okay, and we're going to use that relationship to our advantage because we can skip a whole lot of process in between if we know that we're just going to end up where we started. Okay, so definite integral as a function. Okay. We've talked about how indefinite integrals. Indefinite general integrals are ones where we have no bounds, and we find the antiderivative, and we end up with a plus c. That just represents an area finding formula. We also have definite integrals, where first theorem comes into play, where we take the antiderivative, we plug the upper lower bound in. The number that we get in return is area related. Okay. So now we're going to be looking at some functions that is the integral itself, where the function has a definite integral in it. But instead of going from a constant to another constant, we're going from a constant to a moving value of x. We're really not going to have to visualize and worry about how that's going to look. We just have to kind of know how to change it in terms of how do we find a derivative of something that is in this form. Okay, so that's where second theorem is going to help us out. This applies the concept that derivative and integrals are basically inverse operations of each other. Okay. So we're going to focus on rule number 1. Rule number 2 is really just an adjusted version of 2. But here's the big idea. Let's say we have a function f of t. We apply the integral of that function, and then we turn around and we find the derivative of that result. basically, we're having to do, if we were to do both processes, we're basically moving forwards and moving backwards to where we started. So rather than going through the full process, if we know that we're just doing something and undoing it, we can just jump to the end because we know that we're just going to end up where we started. However, the upper bound will be a variable, and that variable is going to kind of lodge itself into the answer as we go through the process forwards and backwards. So what's going to happen is we can jump to the end, but when we jump to the end, we just have to know what's going to happen with that upper bound. So what's going to happen is that this upper bound, after this whole process is said and done, it's going to get inserted into the function. So every variable that we see initially gets replaced with the upper bound variable. And then this derivative process is also going to have a lasting impact on the upper bound. So we also need to multiply by the upper bound derivative. So it's just a minor adjustment. The function is not going to change much, but then the upper bound is going to have an impact after if we were to go through this full process. But we can skip a lot of the process because of the fact that we know these two operations will just cancel each other out. Okay, so let me show you what I mean by that. We're going to match example 2 with this rule here. So if we want to find the derivative of a definite integral from negative 3 to x, we're just canceling these operations out, and we're just going to follow the rule here. So the rule says f of t turns into f of p of x. So I'm just going to take my upper bound, insert it into the variable. What would that look like if I were to insert x into this expression? So the t gets replaced with what? X. So what would that look like? Plus 4. Yeah, we don't have to do any, the dt is just notation here. We don't do anything with it. We don't do any power rule or anything. Just have to insert that in. So this represents my f of p of x. Multiplied by p prime. X is my p of x, so what's p prime going to be? 1, so times 1. Okay, so right now, it doesn't have much of an impact because it's a, that variable just goes away. So we're able to skip a lot of the process, right? We didn't have to go through a whole power rule, find the antiderivative, and then turning around and finding the derivative. We just jump to the end because we know these two operations will just undo each other. So all we're left with is just square root of x squared plus 4. Okay, questions with A? Okay, part B, same idea here. Derivative, integral, they're going to cancel each other out. We're just going to follow this rule here. So what's going to show up first? Square root of, yep. So everywhere you see a t, replace with x squared. That's my f of p of x. But I also need p prime, right? So what's p prime going to be? Times 2x. That's it. Now, what is something that we did not even look at or not have to involve throughout this problem? The a value, yep, the lower bound. And here's the reason why. The lower bound does not play a role in this process is because, yes, if I were to just do the antiderivative and involve the 3, it's going to give me a number. That 3 will end up giving us a number. But then the derivative of that number will just push it out to what? What's going to be a derivative of a constant? 0. So the lower bound is going to produce a number from the antiderivative process, but then the derivative will just wipe it out to 0. So that's why we go through the second theorem, anything that's a constant as a bound, we know will just go away. So that's why we just completely ignore it. Okay, try part C. Part C should feel very similar to part B. Okay, what did you guys get for part C? Yeah, same as B, right? Even though the lower bound is different, everything is the same, so that just goes to show that lower bound has no impact on my answer here, because it's a constant. Okay, let's look at part D here. Do you notice anything that feels different here with part D? Yeah, the bounds are reversed. Is there anything I can do to make it match the rule that I want to use? Flip it and change the sign, right? So you can always flip the bounds. If you flip the bounds, just know that you are changing the value slightly. So if you want to maintain balance, you flip the bounds and change the sign to ensure that you haven't changed the overall value of your problem. Okay, so I'm going to rewrite the problem here. I'll make the lower bound my constant, my upper bound the variable, but I got to push a negative in front. Okay, so now I can follow the process, right? F of p of x times t prime. Everywhere I see t, replace with 3x. That will represent f of p of x. But then also have to remember that the derivative is going to have an impact on that upper bound, so times p prime. All right, so what do we get? Negative 1 over 3x plus 2, right? Every t gets replaced with 3x. That's my f of p of x times what? Derivative. Post derivative 3x. Just what? There's 3, okay. Yeah, you're doing the antiderivative, okay? So do a little bit of cleanup here. There's my f of p of x, there's my p prime. I can merge those together. Okay, questions so far? Okay, how do we get negative 1? So I had to flip the bounds to get my upper bound to be the variable. But because I flipped the bounds, I got to force a negative outside to maintain balance. So anytime I swap the bounds, I have to make sure I put a negative in front because I'm making everything opposite. Okay, look at part E. What difference do you see here? Two variables, which means that they're both going to have a role. One, the lower bound is not going to disappear like before. So if you look at number 2, this is an adapted version of second theorem, which says that if my upper and lower bound are both variables, I just have to apply the process twice. The upper bound is going to do this thing like how we've seen before, but then we don't want to ignore the lower bound because lower bound is no longer a constant. So we do minus, and then we do the same thing with lower bound. F of q of x times q prime. So we basically repeat the process for both the upper and lower bound and just make sure there's a minus sign separating the two expressions. Okay? So try that. See if you can follow the rule and work that out for part E. Okay, how do your steps look? The match. F of p of x, just insert the x squared in for the t, times upper bound's derivative, minus, okay, we can't ignore the lower bound because it's not a constant, so repeat the process here, insert x in for the expression, we call it f of q of x, so 2x plus 3, times lower bound's derivative, x becomes 1. Good? So now we're just going to clean up. Distribute the 2x through. Questions with E. Okay, anybody still need to look at this? Yeah. Okay, how do we get the derivative? So the derivative, you see that x squared? What's the derivative of x squared? 2x. And then q prime is the derivative of x, which is 1. Okay, so I like for us to practice more with these concepts. So I'm just picking out some problems as examples, as well as some problems from homework. So if you guys can get on a sheet of paper and just copy down number 47 up there, we're going to do average value theorem for 47. Okay, go ahead and set that up. Find the average value first, and then to find the p-value, take that average value and set it equal to the function. Let's see how you guys do with your setup. If you get done with 47, I have a second theorem, number 2, example 2, that you guys can copy down. That is possible. Find any open space that you have, either in your packet or on a separate sheet. Okay, remember, you've got a good power rule for bounds to be inserted into any expression. Feel free to use your calculator. I know some of these numbers are got some messy fractions there. Okay. So now I can just half bracket. Now work the balance. Second here. Okay, let me go through the steps. Seems like most of you guys are on the right track. Okay, so we set everything up first. A and B value gets replaced with -2 and 2. Our function gets replaced with 4 minus x squared. And the first thing we do is we got to take care of that indefinite interval. I know those bounds are tempting you to want to use those bounds, but we're not going to touch those bounds yet. Okay, take care of the 4 minus x squared. So 4 becomes 4x, x squared becomes x cubed over 3, and then the bounds can be involved. Okay, upper bound is 2, lower bound is -2. Insert the 2 in for all the x's. We get 4 times 2 minus 2 cubed over 3 minus big parentheses. And then do the same thing with the lower bound. -2 in for the x, -2 in for the x. You can use your calculator to clean this up. When you clean all that up, it should get you all the way down to 32 over 3. But don't forget, there's still this 1/4 sticking out here. You got to involve this width component. Area divided by the width will get you down to 8/3. That's part A. Part A is the average value across this entire graph from -2 to 2. Average height for all the y values is 8/3. Okay, that's part A. Any questions up to that point? So now part B is finding the c-value. Basically, that's saying, okay, I know the graph is going to hit a y value of 8/3 somewhere along the graph. I'm just working backwards to figure out where's the x value for that location. So if we know the y value, we can just set that equal to the function to solve for the x. No, it's the 4 minus x squared. It's the original problem. Yeah. No, we're not going to use this 4x minus x cubed over 3 anymore. It's just used to work the bounds in, but now we're back to the original problem. Now we're back to the original graph. So we set the original function equal to 8/3. Solve for x. We only care about location in the interval from -2 to 2. But when you get it all the way down, we get plus or minus 4 over root 4 over 3, which is 2 over root 3, and both positive and negative 2 over root 3 are safely between -2 and 2. So we keep both locations. We use both of these values. Yeah, that's fine. Any of those variations are fine. You don't have to get it all the way cleaned up. Okay. Example 2. This is the second fundamental theorem of calculus problem that we just did. Okay. So, try number 2. If you get done with 2, then I have 2 more average value theorem problems to try. These are from the textbook, from the homework problems, 43 and 49. So try.
2x. Oh, is it 2x cubed?
Yeah, it's 2x cubed. 2x cubed is the lower bound. Okay. Does anybody still need number 47 on the board? So here's second theorem. We're going to apply this rule, apply this theorem for the problem. Yes, we do. We do need to swap the bounds out to get that upper bound to be a variable. Yeah. Okay, check your answer here. All right, any questions with 2? Does everybody see the fact that we have to change the bounds, force the negative into the expression, and then work the rest of the problem out. Replace every t with 2x cubed. That's your f of p of x, and then to the side, multiply by 6x squared. That's not too hard.
That final, like the final answer we're getting, that's the integral of that, the first, like, the top is within the bounds.
The result of this is the integral followed by the derivative. So you see how this 2t over 5 minus t squared is not really changing a whole lot. The reason why is because we're basically taking a shortcut. Rather than doing the full integral and turning around and find the derivative, we know because these two operations cancel each other out, we're just going to jump to the end, understanding that this upper bound is going to kind of insert itself into the answer.
How can you use that? What do you use it for?
What do you use this for? So later on, we're going to have some function that's going to look like this, and you're going to be asked to find the derivative of this function. And to find the derivative of this function, we just have to apply this process. So sometimes you have a function that has an integral in it, which looks really strange, and because we have second theorem in front of us, we're able to find the derivative of something that looks as messy as this. Yeah. And there's going to be some response questions that's going to have this kind of a strange form, because you know how to take a derivative of a function that has an integral in it. Okay, so you guys can try 43. For 43 and 49, I just want you guys to find the average value. Don't have to find the C value, just do the average value theorem and find f of C. Okay, so this is 43 from your textbook or from your homework. Okay, 43. Spend the time to get your terms ready for power rule, apply power rule, and then insert the bound. But the bound is not going to be used for what you see in front of you. This is okay. 1/2 times 2 is 1. If I put 2 in here, this becomes square root of 8. The square root of 8 is 8 root 2. Not the root 2. Square root of 8 would be 2 root 2.
Oh, right. This is more highlighted by 1 half. No.
Yeah, you do.
I think it's negative.
You get your x minus 2 root x, get ready for power rule. Once you get ready for power rule, then apply power rule, add 1 to the exponent, divided by the exponent. Then work in the balance. Right? 2 gets inserted first, minus parentheses. The nice thing about the 0 is 0 is going to, in this case, take away all the terms, 0 out the rest of the terms. Now, as you spend your time cleaning up your integral process, don't forget that 1 half is still playing a role, right? That 1 half is going to get multiplied in after you clean up your integral, your depth integral. Okay. 2 to the 3 halves, the same thing as square root of 8. The square root of 8 can be cleaned up to be 2 root 2. So I get 2 minus 8 root 2 over 3. But I have to make sure I involve my width component, so times 1 half. That gets me down to 1 minus 4 root 2 over 3. Right, questions with 43. Okay, one last one here. Average value theorem for sine of x from 0 to pi. As a reminder, the integral of sine is negative cosine. Let's try 49. Last problem. It's just going to find the average value. Okay, 49 just find the average value. Okay, does anybody still need to look at 43? Are we good here? Okay, here's the setup. Sine becomes negative cosine. Then you plug in the upper bound followed by lower bound, right? You don't involve the 0 and pi into sine. You got to take care of sine first before the pi and 0 gets involved. What's cosine of pi? Negative 1 with a negative with a positive 1. Okay, yeah. So these two will cancel out to positive 1. What's cosine of 0? 1. Okay. So this will end up giving us 2. And then don't forget there's that width component. So hopefully we feel a little bit more comfortable with these two processes, average value theorem and second fundamental theorem. Okay, so tomorrow, I'm gonna be checking your homework for the past, for Tuesday and Wednesday. Yeah, question?
I could get it. Oh, that's what I like that.